Welcome back for another video on series. This is our last section in the chapter on power series and Taylor series. So in this section, we want to talk about how to work with different power series, perhaps taking the limit of something that involves a power series, or using a known power series or Taylor series or Maclaurin series in order to find a new series. The other thing that we want to do is we want to develop a new kind of power series, which is a Taylor series called the binomial series. Binomials raised to a power show up in lots of applications in the real world, and we'd like to have a Taylor or Maclaurin series for these as well. So this is what we're going to do in this section, and I hope that you will enjoy me and stick around for the rest of the video. Let's get started. The first thing we want to do is we want to talk about working with Taylor series. So when we're working with series, we're either using a known series to find a new series based on the old one, or we're using it to find the limit of something or something like that. So there are lots of known series. So what are some of these known series? Well, I have a handout that I provide to my students that I'll show you right now that gives some of the more well-known different series. So looking at this one right now, let me share my screen with you so you can see it more easily. Screen 2, there we go. Sharing it now. So when we're looking at this particular thing right here, what you'll see right here are some known geometric series. Now, when we talk about the geometric series, we're really talking about this first one up here. This is 1 over 1 minus x, which we know to be the sum from 0 to infinity of x to the n. We proved that as a geometric series where the common ratio was x. And so we know that it converges provided that the magnitude for x is between -1 and 1. So we have this one already. These second two are actually based on the binomial series expansion later on, but I listed them here because they are types of geometric series. And so they have formulas. 1 over 1 minus x to the second power can be written as the series from 1 to infinity of n times x to the n minus 1. Now, the third one is 1 over 1 minus x to the third. And this series has to start at 2. It cannot start at 1 or 0. And then it has the form n minus 1, the quantity, times n divided by 2, times x to the n minus 2. These are known geometric series, and they converge whenever the magnitude of x is between -1 and 1. Now, we've talked about Taylor series as well in the previous section. So let's review briefly what we mean when we talk about a Taylor series. A Taylor series for a function with center A is given by this polynomial expansion that's infinite, and it is the series from 0 to infinity of the nth derivative of the function evaluated at the center A. Sorry, let me pause this while my dog has a fit. Nothing like a dog to interrupt your train of thought. So we're talking about the nth derivative of the function with the center plugged in. So this is actually a constant divided by n factorial times x minus the center A to the nth power. So the power matches the factorial in the denominator, and the factorial and the power match that derivative that you took. So remember, we developed tables where we computed all the derivatives up to maybe 6 or 7 if we were writing by hand. And then we would compute the derivatives with the center plugged in, and then we'd find the coefficient by dividing those by that value factorial. And this gives you the expansion that you see here on the right. It is infinite. It goes forever. In a sense, it's like an infinite polynomial. And in order to get the Taylor polynomial, you just stop at the nth power. So a polynomial, Taylor polynomial, stops at a particular value of n. Say after 6 terms, you quit. But the Taylor series goes forever. The Maclaurin series really is a Taylor series. It's just that the center is 0. And for many of the known series that we find, what we're actually looking at are Maclaurin series, because the center being 0 is, of course, the easiest one to compute. And so most of the ones that we write down are Maclaurin series. So let's take a look at some of these commonly known Maclaurin series. Again, this is just the center being 0. So here's one for e to the x. Now, it actually turns out it can be proved that the series generated by e to the x, when you find all the derivatives, plug in 0, divide by k factorial or n factorial, and multiply by x to the n, actually converges to that function. So we can prove that this series actually represents e to the x. And it is an infinite polynomial, and its radius of convergence is infinite. In other words, the interval of convergence is the entire real number line. So I can use this Maclaurin series to represent e to the x at any value of x I want, and I'll get exactly what e to the x is. Now, obviously, if we're going to compute it, we're going to have to round off somewhere, so we're getting an approximation, and that means we're really using the Maclaurin polynomial. The same thing is true for the rest of the ones that you see up here. This one is generated by cosine of x, and this series actually converges to cosine of x on its interval of convergence, which is all real numbers, which means that I can find the cosine of any value by plugging that value into this series, this infinite series. And you can see the expansion right here. It alternates. And then I always associate cosine with being an even function because it's y-axis symmetric. And so the powers and the factorials are all even, and the derivatives. Sine, of course, is an odd function. It also alternates in sign, but because it's an odd function, meaning that its origin symmetric, you have to fold twice to get it to lay on itself, then these powers and factorials are all odd, right? And again, its interval of convergence is all real numbers, which is wild. It means that basically I can find the sine of pi over 42 by taking pi over 42 and plugging it in for x and evaluating it here in this infinite polynomial. Now, I would probably get an approximation. I'd probably take it out maybe 5, 6 terms, something like that. It'd probably give me more than the degree of accuracy that I need. This next one down here, of course, 1 over 1 minus x is just a repetition of the one we saw above. This is, in fact, the geometric series, all right, the basic geometric series. And we know that it has a common ratio of x, and it generates this infinite polynomial here. Its interval of convergence, however, is -1 to 1. Remember that geometric series do not converge for values of the common ratio outside of open -1 to 1. I can take this x and I can rewrite it in such a way that instead of having minus x, I have plus x. Well, how do I do that? Well, I'm still using this one, but I write it as 1 minus a negative x. So I'm actually using this one and replacing x with negative x, which generates this series right here. It has the same interval of convergence because it is basically this first geometric series. Let's take a look at some more known series that we have right here. This is one for natural log of 1 plus x. This is the basic one that we tend to write most of the time. The one underneath it, of course, is based upon it. What's the difference? This one has 1 minus x. So we're replacing x with negative x. And when you replace this x with negative x and work out the negative to a power, you end up with this formula here. It also only has an interval of convergence between -1 and 1. But again, we can always shift the center. We can do things in order to shift where it is accurate so that we can actually approximate natural logs at other values outside that interval. We just have to change what's in here in order to shift and change the value of the interval of convergence. And we'll do an example of that later on. Arctangent is one that has a known Maclaurin series. You'll see it written here. It's very similar to the one for sine in that it has these odd powers, but it doesn't have factorials in the denominator. It just has the integer in the denominator. So that's a big difference between it and sine. It also has a far more restricted interval of convergence, -1 to 1. These next three are the hyperbolic functions. So remember that when you're talking about a hyperbolic function, it's really an exponential function. Sinh is going to be e to the x minus e to the minus x all divided by 2. Cosh is e to the x plus e to the minus x all divided by 2. And tanh, of course, is sinh divided by cosh. So these are really exponential functions, but they do have known power series. The first two, for sinh and cosh, have an infinite interval of convergence. So they apply everywhere, which is super, super handy. And these are actually relatively simple formulas. Again, it's much nicer to work with a polynomial expression than it is to work with something like e to the x plus e to the minus x all divided by 2. I mean, that's not going to be fun to work with. Tanh, of course, has a more complicated one, and it has this b sub 2n, which actually represents a Bernoulli number. We're not going to cover what Bernoulli numbers are, but you can find them if you want to Google them. So these are some of the known Maclaurin series. The last thing we're going to talk about today is what's actually called a binomial series. And a binomial series, as you would expect, is based on the binomial 1 plus x raised to a power. So the power in our case doesn't have to be a whole number. Now you can use it for a whole number, then it terminates, it actually becomes a finite expansion, it doesn't go forever. But if it's not a whole number, let's say it's raised to the -3 power or to the 4/5 power, something like that, then it becomes an infinite polynomial similar to what we've seen above, right? And so these types of binomials raised to a power, they come up in all kinds of applications. So it would be super handy to have a power series to represent them. And this is actually a power series, and it is in fact a Maclaurin series. It is also centered at 0. And we'll be studying these later in this section. So these are some of the known power series, the most common ones that you might be working with. And what I'm going to do in this particular section is, if we need one, I'm just going to copy it from the table for you so that you don't have to go hunt for it, all right? So the first thing we want to do is we want to find the Maclaurin series for x sine of x using the known Maclaurin series for sine of x. So this is one of the ones that we had in our table up above. Again, remember that sine is an odd function, meaning that you have to fold twice to get it to lay on top of itself. All right. And so you see that we have these odd powers here and odd factorials. Both sine and cosine alternate in sine. So you see this alternation of sine. And here's the Maclaurin series for it. And again, we could develop this if we wanted to by finding all the derivatives of sine, then evaluating them at 0, and then dividing by that factorial. Remember that with sine and cosine, you get this a lot of cancellation because the sine of 0 is 0, right? So every other one kind of tends to 0 out, which is why you have this sort of every other one pattern here. We want to find x sine of x. So what we can do is we can write x sine of x, which is going to be equal to x times this series from 0 to infinity of -1 to the nth power, x to the 2n plus 1 over 2n plus 1 factorial. Now, are you allowed to pull the x inside the series? Yes, you are, because the x, as far as the series is concerned, is sort of like a constant. It's not what the series depends on. The series depends on the index, which is n. We also use k a lot, so don't be surprised if I switch to k at some point. So the x can just come inside here, and that gives me x times x to the 2n plus 1. And so the next thing that I can write is that this is equal to the series from 0 to infinity of -1 to the n, x to the 2n plus 2. Now, why 2n plus 2? When the bases are the same and you're multiplying, you add the powers, and the power on x is 1, and 1 plus 2n plus 1 is 2n plus 2. Now, you could just leave it like this. This is a new Maclaurin series, but it's a Maclaurin series for x sine x. It's going to have the same interval of convergence. that we see right there, but you could also, and sometimes it does come in handy to rewrite it in a slightly different form. I don't require my students to do this, but sometimes it is helpful. And that is to factor the 2 out of the 2n plus 2 and to think of it as x squared quantity to the n plus 1 power. Remember that when you have one base that has 2 powers on it, you multiply the powers. So this would generate 2n plus 2 again, right? And that's it. There's nothing more to doing this. It's really relatively straightforward. You're simply finding a new Maclaurin series for x sine x using the known Maclaurin series for sine of x by multiplying by x. That's it. And your interval of convergence is going to be the same. Now let's take a look at this example, which is to find the Maclaurin series for x squared e to the negative x. Now this one is going to be a little bit more complicated because we don't have e to the x, we have e to the negative x. So we're first going to have to change the e to the x to e to the negative x, and then we'll multiply it by x squared. So let's take a look at what we want to do with that. So first things first, we want to replace x with negative x, all right? And then we'll multiply by x squared. So I'm writing out in words what my plan of attack is, all right? So the first thing I'm going to do is I'm going to say x squared e to the negative x is equal to x squared times the series from 0 to infinity of, I'm going to replace the x with negative x. So I have negative x to the nth power over n factorial. Now we typically want to pull the negative off of the x. This is like a -1 times x. So I can rewrite this instead as x squared times the sum from n equals 0 to infinity of -1 to the n x to the n over n factorial. And then just like we saw last time, the series only depends on the index n, so it doesn't depend on x, so I can pull the x squared inside. And then I have 2 things with base x multiplied, so I add the powers 2 plus n, so that will give me n plus 2. So this then becomes the series from n equals 0 to infinity of -1 to the n x to the n plus 2 divided by n factorial. And that's it, all right? That's all you have to do. I know you're at home thinking, that's too easy, there's got to be a catch. This last section is actually somewhat simpler than what we've done before. There is a bit of harder material when we get to binomial series, but the beginning part of this, using known power series, really is pretty straightforward. Now let's take a look at the next example, which is to find a Maclaurin series for the sine of pi x divided by x cubed. So again, we want to use the known Maclaurin series for sine x, which I've reproduced for you here. We want to replace x with pi x. So that's going to be our first step. Replace x with pi x. And then we're going to divide by x cubed. All right, so that's our plan of attack. So we have the sine of pi x divided by x cubed has to be 1 over x cubed, leaving that on the outside for now, times the series from 0 to infinity of -1 to the n. And then I'm going to replace the x with pi x. The power is 2n plus 1 over 2n plus 1 quantity factorial. Now, again, just like I pulled the -1 off of the previous x, I want to pull the pi off the x. I want to be able to combine my x's together. So the next thing I'm going to do, I'm going to leave the 1 over x cubed outside. And I have the series from 0 to infinity, -1 to the n. I'm going to write this as pi to the 2n plus 1, x to the 2n plus 1. And I'm going to divide that by, 2n plus 1 factorial, right? So I'm separating the pi to the power from the x to the power. Remember, if you have a power outside a product, then the power applies to every factor on the inside. This is algebra. All right, so we get this relationship here, and then I can divide by x cubed. Now, if the bases are the same and we're dividing, then we subtract. So we take the numerator power, 2n plus 1, and we subtract 3, which would give us 2n minus 2. So this is going to give me the series from 0 to infinity of -1 to the n, pi to the 2n plus 1 power, and then I'm going to have x to the 2n minus 2 power divided by 2n plus 1 factorial. And again, 2n minus 2 has a common factor of 2. So it might be helpful, depending on what you've got later on, especially if you're checking an interval of convergence, it might be helpful to write this in a slightly different form, which is to write this as x squared to the n minus 1, all divided by 2n plus 1 quantity factorial. All right. But again, that's sort of a personal choice, and sometimes it's useful and sometimes it's not. So this is also just fine to leave it in this format right here. Okay. We have another one that we want to take a look at, which is example 4. When we're looking at example 4, we now want to use two different Maclaurin series, known series for sine and cosine. And we want to actually use the series to prove that the derivative of sine of x squared is 2x cosine of x squared. Now, we know we can get this using the chain rule, but we want to prove it using power series. So the first thing we need to do is we need to find the sine of x squared as a power series, specifically as a Maclaurin series. And then we'll take the derivative of it in series form. So the first thing that we're going to do is we're going to replace the x with x squared. So we're going to find the sine of x squared by using the known power series. So the series from 0 to infinity, -1 to the n, replace x with x squared to the 2n plus 1, all divided by 2n plus 1 factorial. Okay, so far so good. Now I want to prove that the derivative is this in power series form. So I'm going to have to take the derivative of this, and it would be helpful to go ahead and have these multiplied out so I can use the power rule. So 1 base, 2 powers, I multiply the powers. So this then becomes, I don't know if I have enough room to write it here, but I'll try to squeeze it in. I need to write smaller. -1 to the n, x to the 4n plus 2 over 2n plus 1 quantity factorial. So the next thing we want to do is we want to actually take the derivative of this in our Taylor series form, right? The Maclaurin series. So we have sine of x squared, which is going to be the derivative with respect to x of this series from n equals 0 to infinity of -1 to the n, x to the 4n plus 2 divided by 2n plus, oops, lost my n, plus 1 factorial. Lots of writing in this particular section. Okay, so to take the derivative is with respect, so it doesn't affect n. So I can slide this inside and I can apply the power rule, which is basically going to give me the series from 0 to infinity. The -1 to n is a constant. The 2n plus 1 factorial is a constant, doesn't depend on x. The only thing that depends on x is x to the 4n plus 2. And the derivative of that would be pull the power to the front, 4n plus 2, times x to the 4n plus 2 minus 1, which would be 4n plus 1, right? Now, what could we do from there? Well, the next part is mostly some manipulation, algebraic manipulation. We're trying to get it to look like 2x cosine of x squared. So some students would stop right now and they would use the known Maclaurin series for cosine and compute the Maclaurin series for 2x cosine of x squared, and they would compare it to what they had here and try to get one to look like the other. All right. I, however, think we can do one more thing to make this a little bit simpler. This 4n plus 2 has a common factor of 2. So if I write it up here, this becomes 2 times 2n plus 1. Oh, hang on a minute. I've got 2n plus 1 factorial in the denominator. So the next thing I'm going to do is I'm going to expand this a little bit. So this is going to become the series from n equals 0 to infinity, -1 to the n. It's lagging a little bit. Let me see if I can speed it up by saving. And then I've got times 2 times 2n plus 1 times x to the 4n plus 1 divided by, now I'd like to cancel this 2n plus 1 with the 2n plus 1 down here, but this one's a factorial. So I need to back it down one level. So this is going to be 2n plus 1 times the quantity 2n factorial, right? Remember, you're subtracting 1 from the inside, and that would be the 1 right in front of it. Then the 2n plus 1s will cancel out. And finally, I can write this in this format. The series from 0 to infinity of -1 to the n times 2 times x to the 4n plus 1, all divided by the quantity 2n factorial. Now note that this 2 does not have the power 4n plus 1. It's only applied to the x, which is one of the reasons I used a center dot in between them just to emphasize that. The power on 2 is 1. All right, now let's go ahead and find the power series for 2x cosine of x squared and compare it to what we found below. So now we're going to find that next part. Let me do this in gray. So we're going to find 2x cosine of x squared, which is going to be 2x times the series from n equals 0 to infinity of -1 to the n. Now I need to replace my x with x squared because I'm trying to find the power series for cosine of x squared. So I have to replace that x with x squared. So I get x squared to the 2n power divided by the quantity 2n factorial. Now, x to the second power raised to the 2n power, 1 base, 2 power, so you multiply the powers, which will give me the 4n power. So this gives me as the next step 2x times the sum from 0 to infinity of -1 to the n, x to the 4n over 2n quantity factorial. Now, the next thing that you can do, the 2 is a constant and the x does not depend on the index n, so these can be pulled inside. I have x times x to the 4n, which is going to give me x to the 4n plus 1. So I have the series from 0 to infinity, -1 to the n. Here's my 2. Here's my x to the 4n plus 1, all divided by 2n quantity factorial, which is exactly what I found previously when I took the derivative in the Maclaurin series format, all right, of sine of x squared. So we proved the chain rule using power series. Okay, let's use this to do a different kind of problem. We're going to use the known series now to solve a differential equation. So we've talked about differential equations before. Remember, differential equations, you have some relationship between one or more of the derivatives of a function and the function itself, but you don't know what the function is. You don't know what y is. Y equals f of x, but what is that? What equation is it? So we're going to solve this differential equation, y prime equal 2y, with the initial value that when the independent variable is 0, y is 5. And we're going to do this by using a solution of the form of a power series from n equals 0 to infinity of c sub n x to the n. So it is a power series, right? You see the x to the n here inside the series. That makes it a power series. And we're going to find out what the coefficients need to be for this to solve this equation. And you may be going, I have no idea how to start. Let's start with the differential equation. The differential equation says y prime has to equal 2 times y, and this is my y, all right? So the first thing that I'm going to do is I'm going to write out what y is, write out a few terms of y. So I have y as a function of x is equal to this sum from n equals 0 to infinity of c sub n x to the n. And this becomes c0 x to the 0 is 1 plus c1x plus c2x squared plus c3x cubed plus dot dot dot. It keeps going forever, right? I mean, this is basically my test function. Well, the first thing I can figure out is I can actually figure out what c sub 0 is right away, because y of 0 is equal to 5. So if I were to replace x with 0, all of these terms would drop out and I would get c sub 0 equals 5. So I know that from the get-go, which means that I now have 5 plus c1x plus c2x squared plus c3x cubed plus dot 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 dot. All right. Now the next thing I want to do is I want to find the derivative. I've used the initial value. I've pinned down the value of c sub 0, but I haven't used the differential equation. So let's go ahead and find y prime in this format, and then we'll use it in order to set it equal to 2 times this. All right. Now, y prime, I can do it in either series format or I can do it in this format right here. When you do it in series format, be careful. When you take the derivative of something that starts at 0, where your first term is a constant, when you take the derivative, what's going to happen to the constant? Yeah, it's going to go away. It's going to be 0, which means that your subscript is going to have to start at 1, not at 0. So for example, if I want to write down what y prime of x is going to be, this is going to be this sum from n equal 1 to infinity of n c sub n x to the n minus 1. All right. So I'm taking the derivative of this with respect to x. So I pulled the power to the front, reduced the power by 1, but my first term zeroed out. So I no longer start at 0, I start now at 1. Now let's go ahead and write out what this would be in terms of the infinite polynomial form. So when I take the derivative of 5, I get 0. So then I get c1 plus 2c2x. What happened to my 2? I don't know. Plus 3c3x squared, and let's do one more, plus 4c sub 4x cubed plus dot dot dot, right? So we've got some terms down here that we can kind of see what they look like. All right, so this is what it looks like in power series form, and this is what it looks like in the expansion form. Now we want to take this and set this equal to 2 times y. So I'm going to write these out in their expanded form. So I have c1 plus 2c2x plus 3c3x squared plus 4c4x cubed plus dot 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 equals, now I've got to take y, which is here, and multiply by 2. So this is going to become 10 plus 2c1x plus 2c2x squared plus 2c3x cubed, and that's probably good. All right, so this is using the actual differential equation. So this is y prime equal to 2y. All right, I've already used the initial condition. Unusually, I used it first and found the value of c sub 0. Now, for these polynomials to be equal to each other, they're infinite polynomials, but to be equal, their coefficients of like terms have to be the same. So this constant has to be equal to that constant. There are no other constants because the powers are increasing, they're power series. And this then allows me to write down that C1 has to equal 10, All right. So that's by equating the two constants that you see here. So this constant has to be equal to that constant. Well, what about the x terms? Well, the x terms right here tell me that 2c2 has to equal 2c1. So I'm going to do that one next. 2c2 has to equal 2c1 because they're both the x terms. But the 2's would cancel, and this would just give me that c2 equals c1, but c1 is 10. So now I know that c2 is also 10. All right, we can continue in this fashion. Let's take a look at the next one. We have 3c3x squared, which has to be equal to 2c2x squared. So this tells me that 3c3 has to equal 2c2, which means that c3 is 2/3 c2, and c2 is 10. So this is 20 over 3. Right? And let's do our last one that we have to look at here. We find another color to highlight it with. So we'll highlight this one in purple. And when we're setting the like term coefficients equal, we get 4c4 is equal to 2c3, which means c4 is equal to 2/4 c3, which is equal to 40 over, am I doing this right? Over 12, or 4 times 3. Now you may be going, why is she not reducing? Well, as it turns out, when there's a pattern to be found, it is usually more simple to find the pattern. It is not simple to find the pattern, but it's easier to find the pattern if you don't reduce. All right, so I'm leaving this like this, and I'm hoping that I'm going to see a pattern emerging. And in fact, we will see a pattern emerging, but it is not trivial to find this pattern. So let's now go ahead and write down what our relationship for y is. So here's our y right here. Let me see if I can copy that y term. All right, so let's put that down here. Oops, hang on a second. I know exactly what's wrong. Okay. I just have to wake it up a little bit, and then I'll be able to find what I need. Okay, so now we've got our expression for y of x, which you can see right here, and we want to replace c1, c2, c3, c4, and so on with the constants that we found up here. And then we want to see if we can find a pattern, if this is actually some known power series in disguise. So, and in fact, it is a known power series in disguise. So this can then be written as 5 plus c1, looking up here, was 10. So we have 10x plus 10x squared plus 20 over 3x cubed plus 40 over 4 times 3x to the 4th plus ... Okay, so I can see basically what I've got going on right here. Now this 4 times 3 kind of looks like maybe I've got some kind of factorial developing there. So I'm curious to know if the next one would have a 5 times 4 times 3. Okay, so let's come back up here to where we were before, and let's expand this one more set. So what would we have after this one? The next term after this one would be plus 5c5x to the 4th, and this one would be plus 2c4x to the 4th. All right, so that would be our next term there. So equating those two, let's see if we do have a factorial type pattern developing. So we have 5c sub 5x to the 4th equal to 2c sub 4x to the 4th. The x to the 4th, of course, cancel. We're equating coefficients. And so we get C5 is equal to 2/5 C4. But we know that C4 is 40. So I have 80 over 5 times 4 times 3. So I definitely do have this factorial type developing. Now, the problem is that I don't have the 2 and the 1. Now, the 1's no big deal. I can put a 1 times 1 anywhere, so that's not a problem. But I need the times 2. So we're going to play a little trick here to help develop this. The other thing that we note is that all of these terms are multiples of 5. So one thing we can do to make it a little bit simpler so we can see what's left is to go ahead and factor out the 5. So let's factor out the 5 and then we'll play our trick on the next step. So we're going to have 5 times 1 plus 2x plus 2x squared plus, what would that be? 4 over 3x cubed plus 8 over 4 times 3x to the 4th plus 16 over 5 times 4 times 3x to the 5th plus ... Okay, so that's what we've got so far. Now, how can I get the 2 in the denominator so it truly is a full-on factorial? Just multiply by a form of 1. So multiply by 2 over 2, and that will fix it. All right, so what we're going to do is we're going to multiply this by 2 over 2, and that will give me that. And here I could multiply by a 2 over 2 and see if that fits that pattern. And then I'm going to multiply this by 2 over 2, and then I'm going to multiply this by 2 over 2. All right, so let's go ahead and write down what we've got now. We've got 5 times, and I may need another line down here below this. I'm not sure how much extra space I've got, and I know I'm going to need some more. So I've got 1 plus 2x. I'm not sure about those first terms yet. Are they going to fit the pattern or not? I'm not sure. I'm trying to fit it back here, and then I'll work backwards to see if I can make it fit the first couple. So this becomes 4 over 2 factorial x squared. And this becomes 8x cubed over 3 factorial plus 16x to the 4th over 4 factorial plus 32x to the 5th over 5 factorial plus ... Okay, now hang on a second and stare carefully at these constants in the numerator. They're all powers of 2. This is 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, and they match the factorial and the power on x. So the next thing we're going to do is we're going to expand this a little bit, and we're going to write it in a slightly different form. So I've got 5 times 1 plus 2x. I don't know if it's going to fit the first 2, but I'm trying. So I've got 2 squared x squared over 2 factorial plus 2 cubed x cubed over 3 factorial plus 2 to the 4th x to the 4th over 4 factorial plus ... Now, if they're both raised to the same power, I can put 2x in parentheses and put the power outside. Hopefully you can sort of see what's about to come out now. If not, hang on one more step. So we have 1 plus 2x. Still don't know about those first 2 terms, but now I've got 2x squared over 2 factorial plus 2x cubed over 3 factorial plus 2x to the 4th over 4 factorial plus ... Okay. It's time now to see if we can get this pattern because we've got it as simple as we can. Does it fit these first 2 terms? This would become 2x to the 1st over 1 factorial if I pull this pattern backwards. And in fact, it fits. What about the 1? This would have to be 2x to the 0th, which is 1, divided by 0 factorial, which is also 1 by definition. So it fits for the first as well. So let me go ahead and see if I can write down then a series based on the expansion that we see here. So we have a series. We're going to start with n equals 0 and go to infinity. And it looks like we want to have 2x raised to the nth power over n factorial. Now, this is one of the ones that we know. So come over here to your known series and look for one that has that pattern. If you scroll through, you're eventually going to see that this is the pattern for e to the x. It is something to the nth power divided by n factorial, where we've replaced x with 2x. So this must be e to the 2x. So this becomes then 5e to the 2x. In other words, my solution to this differential equation is the equation 5e to the 2x. It is a particular solution because we had an initial value, and this becomes our solution to that initial value problem. Okay, let's take a look at one more example of using known series to find other values. In this particular example, we want to use the known Maclaurin series for sine x, which we've used several times today, to find the limit of x sine of 1 over x as x goes to infinity. Now, we've had to do these before using L'Hopital's rule, because as x goes to infinity, this approaches 0, and sine of 0 is 0. And then x is going to infinity, so we have the form infinity times 0, which is indeterminate. So we've been doing these with L'Hopital's rule. They can also be done using power series. So we're going to use the Maclaurin series for x sine of 1 over x. So first find the power series for x sine of 1 over x. So we're going to replace x with 1 over x, and then we're going to multiply through by an x. So I have the series from 0 to infinity of -1 to the n, replace my x with 1 over x, raise it to the 2n plus 1 power over 2n plus 1 quantity factorial. Now, 1 to a finite power is just 1. So 1 to the 2n plus 1, which is finite, becomes 1, and this becomes x to the 2n plus 1 in the denominator. So this gives me x times the series, -1 to the n, divided by x to the 2n plus 1 times the quantity 2n plus 1 factorial, right? So I have that. Now I want to multiply through by x. Well, what's going to happen is this x on top is going to cancel one of the x's on bottom. And so I'm going to end up with the power series, the Maclaurin series, centered at 0, of -1 to the n divided by x to the 2n times the quantity 2n plus 1 factorial. Okay, so I have this expression, and what I want to do now is I want to use that Maclaurin series in the limit. So I'm going to go ahead and write out what it is. So what I want to find now is the limit as, what was my limit again? X goes to infinity of x sine of 1 over x becomes the limit as x goes to infinity of the series from n equals 0 to infinity of -1 to the n over x to the 2n power times the quantity 2n plus 1 factorial. Now let's expand it term by term. Usually you don't have to expand it too far to see what's happening. When n is 0, -1 to the 0 will give us a +1. So it's going to alternate signs, but it's going to start positive. X to the 2 times 0 is x to the 0, which is 1. 2 times 0 is 0 plus 1 is 1 factorial, which is 1. So it looks like the first term that we're going to get here is going to be a 1. Then it's going to alternate signs. The next one will be negative. When n is 1, I'll get x squared in the denominator. So I have a 1 in the numerator I have x squared in the denominator. And then when n is 1, 2 times 1 plus 1 would give me 3 factorial. So times 3 factorial. Then it alternates sign. Then I have 1 over, well, basically x to the 2n is going to always give me an even exponent. And this 2n plus 1 is always going to give me an odd value, which is going to be 1 in addition to whatever that even power was. So the next one's going to be x to the 4th times 5 factorial. And then I can go one more, 1 over x to the 6th times 7 factorial plus minus dot, dot, dot. Okay, so it continues in that pattern. Well, if I take the limit as x goes to infinity, then I've got 1 over something that's blowing up to infinity. So I know that this one is going to go to 0. That's going to go to 0. That's going to go to 0. All of these at the back are going to go to 0. But the first term will still be there. And the limit of a constant is the constant. So my limit is 1. And it's really not any more work than doing L'Hopital's rule. It's about the same amount of work. It's just a different method of finding it, right? So this sort of concludes the first part of this section, which is talking about ways of working with Taylor and Maclaurin series in order to find new series or to evaluate limits. The next thing we want to do is we want to talk about binomial series.